Hi, my name is Hamid Bonab. I'm an applied scientist at Amazon. Today, I'm going to present our work titled as Blend and Match, Distilling Semantic Search Models with Different Inductive Biases and Model Architecture. This is a joint work with Ashutosh Joshi, Ravi Bhatia, Ankit Gandhi, Vijay Hugdar, Juhi Naik, Mutasam Aldarapsa, Chunhui Teo, John May, Tarun Agrawal, and Vaslav Petrusek. Here is an oversimplified schema of general search architecture. Search systems are usually built on a two-stage paradigm, matching and then ranking. For a user's query, usually several matching systems work in parallel to filter millions of items into a small match set needed for the downstream ranking system. Usually, semantic matching is deployed to complement lexical matching and behavioral signal. Among different approaches, two widely used semantic matching models are bioencoders, such as DSSM, and extreme multi-label classification approaches, such as PECOS. Due to latency and memory constraints in production, it is usually not possible to simultaneously deploy both of the models. However, each of these models provide different predictions that make them more preferred against the other in different stores. In our work, we focus on these two widely deployed semantic matching model architectures at different stores and aim to blend them into a single model to reduce the cost and complexity of semantic matching. To provide the context on our study, we first briefly summarize PECOS and the bioencoder model that we use. On the left side, you can see the PECOS model architecture. PECOS, which stands for Prediction of Enormous Correlated Output Spaces, provides a hierarchical architecture for a multi-class classification problem with extreme output space size, which is in the orders of tens of millions to billions of products. For dealing with this large size of label set, PECOS clusters labels at each depth of the hierarchical architecture and filters large number of labels using one versus race classifiers. For PECOS semantic matching, the query is the input X, and the set of products is the target label set, or Y. On the right side, you can see the bioencoder architecture, which is a metric learning formulation of semantic matching problem. We use a bioencoder model with a triplet loss function. To distinguish our model, we named it bioencoder with triplet loss, or BETL in short. Other loss functions, such as contrastive loss, also can be used here with some modification to the blending loss. For training, we use a two-stage procedure. We first train the model using a pointwise MSE loss with random negative sampling, and then we continue training with in-batch negative sampling and a pairwise triplet loss. Here is the general schema for our blending framework. We start with a pre-trained bioencoder semantic matching model as the primary model and propose a null loss function to incorporate PECOS predictions as the secondary model. Our main motivation is to improve the recall of the bioencoder models in production by incorporating PECOS predictions. We aim to modify the primary model training such that it can incorporate the predictions of the secondary model along with the true labels during training and ultimately provide a single unified model that can be shipped into production, providing the best of the both worlds. Our choice for the primary model is mainly due to bioencoders, simpler architecture, easy maintenance, and less deployment overhead. As mentioned earlier, any model can be used as a secondary model in the framework, and our choice is mainly based on production. Our task is similar to the distillation literature, with the differences that one, we do not aim to reduce model size, and two, the student model, which is named as the primary model, is a totally different problem formulation compared to the teacher model or the secondary model. We designed a pairwise triplet loss function to blend the PECOS predictions into our BETL training. We further fine-tune a pre-trained Beetle model using the proposed loss function. Lambda in our formulation is the interpolation parameter between the original loss and the blending loss term. Our sensitivity analysis suggests best performance with lambda equal to 0.5, which is equal importance. With our blending loss function, the original loss term on the left side maximizes the distance between a positive and negative item, while blending loss term minimizes the distance between the primary and secondary models predictions for a positive item. For our experiments, we use 1 year of behaviors data from 2 Amazon stores, 1 English-speaking store and 1 non-English-speaking store. 5% of queries are reserved for our offline evaluations. We report recall at 100 for these queries as our main metric due to the importance of recall for match set construction. We also report precision, which for that we randomly selected 200 queries and annotated top 16 products for each model. In terms of our baselines, we use Beetle and PECOS as the obvious comparison points. In addition, we adapt the loss function proposed by Hofstadter et al., named as margin MSE. The loss function utilized the margin between the positive and negative samples of the teacher model, and it has been shown to perform better than other existing loss functions when the architecture of the models are different. We also adapted the baseline loss function from Hofstadter. This is a standard distillation loss function already used by many other studies. Here is our main experimental results. As you can see, PECOS has a better recall for both stores. And on the other hand, Beetle provides better precision. We also report the warm-up step results. And as it can be seen, triplet loss is able to improve the performance. Comparing original models with both distillation baselines suggests that for our problem setting, existing distillation approaches might not be that much helpful. And most importantly, our blend and match Beetle model shows large gains in recall over Beetle model with a small loss in precision metrics. All highlighted improvements here are statistically significant using a pairwise 2-sample t-test. Sensitivity analysis of lambda values based on recall for the English store is presented here. Best performance achieved with lambda equal to 0.5, which is equal contribution of the original loss and the blending loss term. With lambda equal to 0, which means no PECOS loss contribution, we only have more training, and it can be seen that there is no effect on the performance. This shows that we are getting the improvement not with more training. When we only use PECOS blending loss term, which is lambda equal to 1, a drastic drop in performance happens. In this work, we presented a blending approach that is able to blend 2 distinct semantic matching models into a single model. Our blending approach is able to drastically improve semantic matching and close the gap between the 2 models. Our key findings are, for different formulation of the semantic matching problem, existing knowledge distillation approaches might not be helpful. PECOS relevant predictions help BM Beetle training, and blend loss function needs to be similar to the model's original loss term. Thanks for listening to our presentation. Please don't hesitate to reach out with any questions or comments.